Whether you're a bioprocess engineer hunting for the perfect scaled-down model, a biotech founder architecting the leap to commercialization, or a scientific analyst who craves raw technical truth, you've reached the technical edge. In this space, we live by a single mantra: the process is the product. Welcome to the Biomanufacturing and Fermentation Technology podcast with Prasad Ernala. Hit subscribe and ring the bell to join a global community and stay at the vanguard of biotech translation. Let's build the bioindustrial future together.
Welcome back to the deep dive. Today, we are walking straight onto the factory floor, mentally at least, and staring up at those massive 2-story tall stainless steel fermentation tanks. Yeah. Huge things. We're talking about industrial biotechnology. And to get our bearings, before we sort of climb the ladder to the top of that tank, I want to start with something, incredibly low stakes. I want you to picture baking a cake.
A classic starting point. Low risk, high reward, usually involves chocolate. I like it.
Exactly. So you mix your batter, you pour it in the pan, you slide it into the oven. The recipe says bake for 30 minutes at 350 degrees. So you set a timer.
Right.
When it dings, you pull it out. But anyone who actually bakes knows the fatal flaw here. I mean, maybe your oven runs hot, maybe the batter was a little cold.
Something's always different.
If you blindly trust that 30-minute timer, you might pull out a burnt brick or a pan of, raw, wobbly goo.
Right. And in your kitchen, the cost of that mistake is what? Maybe $5 and a slightly disappointed family? But let's translate that logic to industrial fermentation, where you're brewing advanced medicines, enzymes in tanks holding 50,000, 100,000 liters. In that context, the raw goo scenario isn't just a bummer, it's a financial disaster.
We're talking millions of dollars in lost raw materials. Opportunity cost.
Easily. And that is exactly what we're unpacking today. We're looking at a set of technical documents focused on engineering harvest end specifications. It sounds dense, but it asks a very simple, very expensive question. How do engineers know when the cake is actually done?
And the big takeaway from all the reading is that the industry is realizing that the timer method, what they call the fixed time endpoint, is, it's essentially dead. It's a relic.
It is. It works in the lab, because the lab is this controlled bubble. But the shift we are seeing in manufacturing is toward fermentation termination as a controlled unit operation.
Which is a mouthful, but let's break that down. It means moving from just like passive observation, watching the clock tick down, because that's what we did in the pilot plant, to active attribute-based decisions.
Exactly. Because unlike a kitchen, a factory is chaotic. Raw materials fluctuate. The physics change at scale. Things break.
Right.
If you just run for 100 hours because the recipe says so, you're flying blind. You're ignoring the biological reality of what's happening inside that tank.
Yeah.
The cells don't care about your schedule. They care about their environment.
So the mission for this deep dive is to explore how the industry is abandoning Titer chasing, which is just trying to get the absolute most product, regardless of the cost,
right,
and moving toward a more sophisticated framework that balances really 3 things: metabolic performance, product quality, and downstream processability.
And that last one, processability, is the silent killer.
Really?
Doesn't matter if you made 10 tons of product, if the broth turns into sludge and you literally can't pump it out of the tank.
So let's get into the mechanics. The source material outlines this 3-layer decision architecture. I really like this mental model because it feels robust. It's not just one switch, it's a series of checks.
Yeah, think of it less like a finish line and more like a safety net with, say, 3 different meshes. You aren't looking for a single moment in time. You're looking for a productive, quality, stable region. A sweet spot.
A sweet spot where the biology is happy and the economics are optimized.
Precisely.
So let's start with layer 1. The text calls this the primary trigger. It's fast, it's online, and it's omnipresent.
Right. This is the industrial backbone. In a massive fermenter, you can't act on data that takes 4 hours to get back from the quality control lab. You need to know what's happening now. So layer 1, it relies on gas exchange metrics.
The acronyms we see everywhere in the literature: our, CER, and RQ.
Exactly. Our R is oxygen uptake rate, how fast the bugs are consuming oxygen. CER is carbon dioxide evolution rate, how fast they're exhaling CO2. And RQ, the respiratory quotient, is just the ratio between the two.
Okay, so why are these a primary trigger? Why not something more direct, like measuring sugar levels or product concentration?
Because gas analysis is non-invasive and it's continuous. You're measuring the exhaust pipe, essentially. You don't have to touch the sterile broth. And it gives you this global picture of the metabolism instantly.
It's like a pulse check.
It's a pulse check, exactly. If the IUR takes a sudden downshift, it tells you the organism has slowed down. Maybe they ran out of food. Maybe they shifted their metabolism. But if that breathing rate drops, you know the batch is winding down, regardless of what the clock says.
Okay, so layer 1 says, hey, the breathing changed, we might be done. But we don't just hit the stop button there. We move to layer 2.
Quality confirmation.
Quality confirmation.
Right. Layer 1 is fast, but it's kind of generic. It tells you the biology slowed down, but not why or what condition the product is in. Layer 2 is slower. It's usually at line, meaning an operator pulls a sample and runs a test right there on the floor.
And this is where we check if the product is actually any good.
Yes. This anchors the decision to what we call recoverable product. You might have a tank full of biomass, but is the enzyme active? Or is it just dead protein or impurity spiking? Layer 2 confirms that the stop signal from layer 1 is actually a harvest signal.
And not just a pause or a glitch.
Exactly.
Then we have layer 3, the stop-loss guardrails. This felt like the emergency brake on a train.
That's a great way to put it. That's exactly what it is. These are risk containment triggers. Even if layer 1 says keep going and layer 2 says product looks okay, if layer 3 goes off, you abort immediately.
So what triggers an abort like that? What's a catastrophe?
A rapid decline in viability cells just dying en masse, or foam escalation. If foam starts pouring out of the vents or the pH starts drifting wildly despite your controls, you cut your losses. You harvest now to save whatever you have.
It's interesting that foam is considered a data point here. I always just think of it as, a nuisance, a mess.
Oh, in this context, foam is high-fidelity data. We can touch on this more later, but rising foam usually means proteins are leaking out of cells. It's a huge distress signal.
Okay, so that's the architecture. But reading through the sources, what struck me was the emphasis on noise. I mean, anyone who works with data knows it's messy, but in a factory, it seems aggressive.
It's a war zone for sensors. A probe might drift. A bubble might hit a sensor and cause a temporary spike. A feed pump might pause for 10 seconds. If your automated system reacts to every single blip, you're going to stop the batch way too early.
And the solution they propose is persistence windows. I love this concept. It's basically telling the computer, don't panic yet.
Right. The rule shouldn't be stop when the RR drops. It should be stop when the RR drops and stays down for, say, 60 to 100 minutes. You have to verify it's a biological trend, not just some mechanical glitch.
And connected to that is event annotation. This feels surprisingly human for such a high-tech process.
It is human. It's about context. If an operator walks by and manually adjusts an airflow valves, the sensors are going to go crazy. If you don't annotate that event, if you don't tell the system, hey, ignore this, we did it on purpose, the algorithm will think the cells are dying.
It prevents false positives.
Exactly. And the text warns about a specific failure mode here called overfitting.
Which is the classic lab-to-plant problem.
It is. In a university lab, you have pristine conditions.
Yeah.
You can use these fragile, expensive sensors that give you perfect data. But you cannot put that delicate glass probe into a 100,000-liter vibrating steel tank.
It'll shatter.
It'll shatter. Or it will foul up in an hour. So if your harvest strategy relies on a sensor that fails 50% of the time, then you don't have a strategy. You have a gamble.
You need robustness over precision sometimes.
You really do.
So let's move into the engine room of the cell. Section 3 covers metabolic and kinetic indicators. This is where we get into the nitty-gritty of performance. And there's a metric here that seems to be a favorite of biochemical engineers, QP-specific productivity.
This is crucial. Titer tells you how much product is in the tank, total. QP tells you how fast each individual cell is making that product right now.
Why does that distinction matter? I mean, if the total amount is going up, why do I care about the rate per cell?
Because you can have a high titer, but a crashing QP. It tells you the engine is sputtering. The signal we look for is a reproducible decline, diminishing returns. If you wait until this total titer flattens out, you've likely waited too long and wasted a lot of resources.
The sources suggest using a rolling window QP, so looking at the last, 4 to 8 hours?
Right, rather than the average for the whole batch. If you look at the average, the history of the batch hides the current problem. You want to see the slope of the line right now. If the specific productivity drops below a certain threshold, the cells are basically telling you, we're tired, we're done.
Okay. Then there's yield erosion. This sounds like finance diminishing returns on investment, but for biology.
It's efficiency. Yield is just product produced per unit of substrate consumed. For every gram of sugar I feed the tank, how much product do I get back?
And if that number starts to drop,
It means the cell is wasting energy. It's shifting energy to maintenance. It's trying to repair its cell walls, balance its pH, just stay alive. It's not making your product anymore. It's just burning cash to keep the lights on.
but the text highlights a huge decision trap here. This was a real aha moment for me.
Yes. This is where you separate the novices from the pros. Sometimes yield drops, not because the biology is finished, but because of a mass transfer limit.
Meaning the tank literally can't push enough oxygen into the liquid. The cells are suffocating.
Exactly. They're gasping for air, so they slow down. If you interpret that as the batch is done and harvest, you're leaving money on the table. The solution there isn't to stop. It might be to increase the back pressure in the tank to force more oxygen in. You have to know if you hit a biological wall or a physical wall.
Okay, let's pivot to section 4, product-centric harvesting. The headline here is, Titer is necessary but not sufficient.
This is the battle cry of the modern process engineer. For decades, everyone just wanted high titer, more grams per liter, period. But the sources point out a dangerous reality. You can have more product, but less usable product if you wait too long.
Because the product starts to break down.
We call it functional quality. This is huge for enzymes. I mean, these are fragile, complex, folded proteins. If you leave them in that soup too long, exposed to heat, shear forces, proteases, they degrade. They lose their specific activity.
So you might have 10 grams of protein, but only 5 grams of it actually works.
And the customer only pays for the ones that work. So harvesting at peak titer might actually lose you money if half of it is inactive garbage.
And there's also the issue of impurity trajectory. The text mentions something called inflection harvesting.
This is about playing defense. Impurities, things like host cell proteins, DNA, lipids, they don't usually accumulate in a straight line. They stay low, and then bam, an inflection point. They spike suddenly.
Usually because cells start popping open, right? That's lysis.
Exactly. When a cell bursts, it dumps all its guts into the tank. And DNA is sticky. Proteases chew up your product. It's a mess.
And the sources call this pre-programming downstream failure. That is a heavy phrase.
But it's accurate. Fermentation isn't an island. If you chase titer until you hit that impurity spike, you have handed the filtration team a tank of glue. They literally cannot filter it. The filters clog, the pressure spikes, you lose the entire batch.
So the strategy is to harvest before that inflection point, even if you could theoretically make 5% more product.
It's a trade-off. You sacrifice a little bit of quantity to preserve all of the quality and processability.
This leads perfectly into section 5. Physiology and secondary signals. We're basically trying to read the cell's stress levels to predict that explosion.
The ultimate guardrail is viability. If the percentage of live cells drops, you are entering the danger zone.
And the source distinguishes between intracellular and secreted products here.
It's a matter of geography. If the product is inside the cell intracellular, you are on a very tight timeline. You need to harvest while the cell is still a tough, intact little package. If the cell breaks, you lose the product into the soup, and it's diluted forever.
And if it's secreted?
You have more wiggle room because the product is already out in the liquid. But you still don't want the cell to burst because, again, it dirties up the water with DNA and enzymes that attack your product.
We touched on foam earlier, but there are other secondary signals too, like pH.
pH is fascinating. In a fermentation, you usually have to keep adding base-like ammonia to keep the pH steady because the cells are producing acid as a byproduct.
So what happens at the end?
A base consumption collapse. Suddenly the pump just stops running.
Right.
The cells stop making acid. That silence is a screaming signal. The metabolism has shifted. It's over.
And metabolic heat.
Same principle. Fermentation generates heat. That's why the tanks have cooling jackets. If the cooling water valve starts closing because the tank is cooling down naturally, it implies the metabolic furnace is turned off. It corroborates all the other data.
I want to ground this in the real world. The sources give us 2 distinct industrial case studies. Let's look at case study 1, amino acids, specifically Corynebacterium glutamicum.
Ah, yes, the workhorse of the industry. This case study is a perfect example of the multivariate approach. They don't look at just one number.
Okay, so what's their specific trigger combination?
It's a triad. First, they look for that reproducible QP decline we talked about, the cells slowing down. Second, incremental yield erosion. And third, and this is specific to amino acids, they check a residual carbon threshold.
They want the sugar level to be low.
Very low. And this isn't just about cost, it's about the next step. crystallization. If you have too much leftover sugar in the broth, the amino acids won't crystallize properly. You get these sticky, impure crystals.
So the harvest point is an optimization of effective productivity and downstream purity.
Exactly. If they harvested earlier, they'd waste sugar and get less product. If they harvested later, the yield would drop and the crystals would be dirty. They find the intersection.
Okay, case study 2 is fungal enzymes. Now, fungi are different.
Very different. They're filamentous. They grow like long hairs or roots. They make the broth incredibly thick and viscous.
So for them, the strategy is harvest at peak-specific activity.
Right. You want that enzyme fresh. But the stop sign here is often physical. It's an operability transition.
Which means the liquid physically changes.
Yes. The viscosity rises. Foam escalates. If you wait too long with a fungal fermentation, the broth becomes like oatmeal. You physically cannot pump it out of the tank.
And the source mentions that extending the run might increase total protein,
But the product quality drops because of proteases, and the harvest efficiency. How much liquid you can actually recover plummets because it gets stuck in the filter. So you harvest early to ensure you can actually process the material.
it really reinforces this idea that the end isn't a simple time on a clock, it's a complex decision matrix.
That's the core message.
Yeah.
The optimal endpoint is an intersection. It's where productivity, quality, and downstream operability all overlap. If you miss that intersection, you lose value.
So, summarizing the big shift here, we are moving from setting a timer to attribute-based control.
We are moving from hope to engineering. We aren't hoping the batch is done. We are measuring that it is done based on the attributes that actually matter, quality and processability. It's all aligned with quality by design, or QBD principles.
And it requires discipline. You need those persistence windows to filter out the noise. You need to annotate your events so the computer knows what's real.
And you need to accept that Titer is not God. Quality is God.
I want to leave our listeners with the provocative final thought from the source material. It discusses a translation gap.
Yeah, this is the challenge for everyone listening who works in this field. We have incredible high-resolution diagnostics in the lab. We can measure everything, but we can't put those delicate instruments in a factory.
So the challenge is?
The challenge is translation. How do you take those rich, complex biological signals you see in the lab and reduce them to a small, robust set of triggers like OUR, pH, or foam that work in a noisy, vibrating, messy manufacturing plant without losing the nuance?
How do you embed the sophistication of the lab into the brute force of the factory?
That is the question. The engineers who solve that translation gap are the ones who will define the next generation of biomanufacturing.
Something to chew on next time you're checking your oven. Thanks for diving in with us.
Always a pleasure.
Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala. Thanks for listening.